Okay, let's start. Good morning. So on Friday this week we have our first midterm, and on Wednesday's class we're going to do a review. Please come to that review with some questions so that we can discuss things. I'd rather have you ask questions and then we can sort of discuss those instead of me telling this or that topic. And today and tomorrow I'd like to just talk about a little bit about this computer graphics and how linear algebra is sort of like a very applicable, very important tool. And of course, computer graphics is a huge topic. It's a discipline. So I'm not going to be able to do much justice to it. We're just going to sort of talk about certain things. Really, I'm using computer graphics to discuss this affine transformations and affine subspaces in more depth. Okay? But let's start slow. As I understand, and I don't know much about these things, okay? I've been educating myself, but take all of this with a grain of salt. As I understand, there are three main steps in computer graphics, okay? One is vertex shading, second is rasterization, and third is fragment shading. And we're really going to focus on this first step, but let me just mention what these seem to be. So you have a world, let's say it's a 3D world or a 2D world, and in it you have a bunch of objects. So you have objects like this. Let's say it's a cube, or a cylinder, and so on. So first of all, you want to model these objects somewhere else, not in the world itself, because, for instance, you want to sort of come up with this model once, and then you want to sort of keep applying certain transformations to put it here or there, or you want to copy it here and paste it there, and so on. And so, first of all, you would like to be able to take this model object, and you want to be able to scale this first of all, and rotate it in three-dimensional space, and also you want to be able to translate it, okay? So, want to be able to scale, rotate, and translate. Now we saw versions of these two in 2 dimensions, right? These are sort of diagonal matrices, and these are the rotation matrices. We didn't really talk about translations. And we'll talk about that in this today and tomorrow. I should also mention, when we're talking about this object, what you really do is obviously not sort of keep in mind or keep track of every single point like you would do in real life, but rather you keep track of the points, of the corners. So let's say, for instance, you call this 0, 0, 0, and then this is, let's say, what is this? So let's say this is in y, so this is 1, 0, 1, 0, and then let's say this is minus 1, 1, 0, and so on. Okay? So this is the model, and then you want to be able to take this model, put it into three-dimensional space, move it around, scale it if you need. So this has length 1, for instance, in the model, but maybe you need really a cube of length, of side length 1/2 or something. And also you want to be able to move it around so that perhaps maybe this is a cube that is sort of standing on top of this corner. So it's like this, and it's sort of rotating perhaps. That's the first step. And then another thing you would like to be able to do is to once you put these objects in your 3D world, you want to have a camera, and you want to project whatever is the view onto the screen. Okay? And able to project onto the screen. That's what you're going to display to the user. Say this is sort of like a video game, or maybe it's a sort of digital experience or something. This has computational costs, of course, because when you're trying to render images, you don't want to render things that you're not going to show to the user, because that's like you want to optimize things. These two correspond to the first item. Okay, this is what is called vertex shading. Take vertices of your object, put it in the three-dimensional space in the configuration you want them to be. At this point, I'm not really thinking about the surfaces, and project them onto the field of view, or onto the screen, respecting the field of view. I'm going to draw an example in a second. Or rather, let's do an example like this. So this is a two-dimensional example, for instance. Let's think of the following. Let's say that I have this triangle. And it has three edges, of course. That's the red edge. That's the blue edge. And that's the yellow edge. Okay? And let's, for simplicity, also think of a coordinate system, although that's not going to be too important. Okay? So now, since my world is 2D, I'm trying to imagine how a two-dimensional image would look like in a one-dimensional screen. Okay? So let's say that my camera is here. And it's looking, so it's looking like this. So it can see everything here, but maybe let's say there are other objects here, and you're not going to render them in the screen. And let's say that our screen is like this. Okay? So this is the television of my user, and this is my scene, and I want to figure out how to, so what to show. Well, what I can do is, I can, of course, try drawing lines. Hang on, I want to do it slightly different so that it looks better. I want to use this one. So this is the camera. Okay, and this is my screen. So in my screen, this triangle is really going to look like this, right? So I have this corner here. Sorry, this corner here, this corner here, and this corner here. So let's call these A, B, and C. This is A, this is C, this is B. And here I'm really seeing this edge. And here I'm really seeing the red edge. Okay? Of course, from this perspective, I should not be able to see the blue edge. Okay? The fact that you're not really seeing this blue edge corresponds to the second item. Okay? Once you transfer all these vertices to your screen, you say, next up, which edges do I see that connect two vertices? So that's about rasterization. So maybe I should draw just a picture. So if I were to imagine a three-dimensional cube, I drew it like that a little bit so that the back side is not really that visible. But at the end of the first stage, you don't really see which is at the front and which is at the back. So at the end of the first stage, you're really seeing this. Okay? So when you're doing this projection, what you want to do is you want to keep track of the depth information. You want to say that, oh, this is the backside. And then in the second stage, when you're rendering this picture, you're really not going to render these. You're going to say, oh, these vertices come from places that are closer to my camera compared to, let's say, this vertex that I erased. And that's why I should not really be drawing that vertex on the screen. This is about rasterization. And third, of course, is shading. Okay? You really want to have a light source somewhere, and you want to sort of put shadows. Let's say that your light source is somewhere here, and because of that, I'm terrible at drawing, of course, but your shadow should be somewhere here, and there should be, like some lights bouncing off of the surface of the object and so on. All these are very important operations. We're also not going to, so this is about shadows. This is about light. So the third item is about light. Second item is about what to actually display. Figure out which, or display, so what to display in terms of which part of which object is closer and farther. And first is really about taking certain transformations and applying them to a bunch of vertices. And we're really going to focus on this. It turns out that both these operations, scaling, rotating, and translating, and this projection, what is called perspective projection, is covered, or the mathematical foundations of both of these is affine transformations. Okay? So we're really going to focus on this part. Any questions so far? Yes?
You said that they're affine transformations because they're not transformations on vectors from the origin?
Yes, exactly.
But just because they're somewhere else?
Yes, yes. Any other questions? Okay, so let me so now we can switch to math. So for vertex shading, need affine transformations. And affine transformations are rather very related. They are very, very much related to linear transformations. They are not quite linear transformations. They include a little bit more. Okay, I wrote it here. So by definition, an affine transformation of Rn n-dimensional space is determined completely by one linear transformation L, let me say, affine transformation A by one linear transformation and one vector. B in Rn. And in this case, you would write like this. A of B is the same thing as L of V plus B. Okay? So what does this mean? An affine transformation really is taking a vector, first applying a matrix to it, linear transformation to it, and then adding a fixed vector to the outcome. Okay? So for instance, let me fix B to be 1, 0. So my affine transformation from the plane to the plane does this, right? So A, xy, and my L, let's say, is identity. So this stays the same, but here I'm adding a certain vector. A of xy equals xy plus B is 1, 0. That is to say, this is x plus 1, y. Geometrically, all this does is it takes any point in the plane and moves it to the right by 1 unit. Okay? So if I had started with, let's say, this shape, now it's here. Okay? Now note that this is not a linear transformation. It is very similar. Okay? But it is not a linear transformation. Let me write it here. So A is not a linear transformation. How can I verify this? Any ideas? What can I do to justify this statement that it's not really a linear transformation?
Could you try and like just plug in the vectors 1, 0, and 0, 1?
Exactly. Well, you can do that, but perhaps, yeah, I guess I can do something like this. Let me do something slightly different. Let me see where A takes 0, 0 to. Okay? Well, A takes 0, 0 to 1, 0, because it's shifting it to the right by 1 unit. But then 0, 0 is the same thing as 0, 0 added to itself. Right? In order for A to be linear, it must be the case then that A of 0, 0 equals 2 times A of 0, 0. But that is not the case. A of 0, 0 plus A of 0, 0 is 2, 0. Because it's shifting 2 times. Okay? And this is not equal to this. And in general, note that any linear transformation would have to take 0 to 0. And certainly this affine transformation doesn't do that. So any linear transformation would have to take the 0 vector to the 0 vector. Okay? Any questions about this? Okay. Let's do another example. Let's think of A of xy equals, let's say, 0, 1, 1, 0 xy plus, let's say, 1 minus 1. This is also an affine transformation because it fits the format. So you see, note that whenever I plug in 0, 0 to, as an argument for the affine transformation, the linear part is going to become 0, and then I'm going to get this, the added vector. So I can also think of this added vector as where my affine transformation takes the origin of the vector space. Okay, let me write that. B equals A of 0 is where A takes the origin to. Takes the origin to. Okay? So this is one way of, piece of information that is important. Let's try to draw this. So I started like this, and when I apply A to it, now the origin is going to be sent to 1 minus 1. Okay? It's going to be sent to here. So let's say this is the triangle, the center of my space. The origin of my space is triangle, and now this triangle is here. Okay, that's the first step. But I need to figure out more. And really, I should perhaps draw it like this. Okay. And so now let's do what your colleague suggested. Let me also figure out where the x-axis and the y-axis goes to, right? So A of 1, 0 goes to this. So 0, 1, 1, 0, 1, 0, plus 1, minus 1. Now, I know that this is just the first column of this matrix, right? When I multiply this. So this is 0, 1, plus 1, minus 1. So now this is 1, 0. So 1, 0 is kept at 1, 0. Okay? But now you see the center of your space is here. So this, it got flipped, right? Because this flips the x and y coordinates. But the center is different. So now that arrow becomes this arrow. Recall that this vector, when I'm thinking about these arrows, I'm thinking about where the center of my space is. And I start at that point, and I draw an arrow that ends at this vector. Okay? And let's figure out 0, 1 as well. If I were to plug in A of 0, 1, let me do it here. Well, this is just the second column plus this. So this is 1, 0 plus 2 minus 1. Oh, sorry. 1 minus 1, which is 2 minus 1. So now you see the vertical arrow goes to 2 minus 1. Because this was 1 minus 1, so this is 2 minus 1. Turns into this. Okay? So this affine transformation really flips or reflects the plane along y equals x and then translates it to this point. Okay? Does this make sense? Good. And just like we did for linear transformations, we would like to be able to talk about composite affine transformations. I want to say I want to say something like, let me first apply this affine transformation and then apply this other affine transformation. Okay, let's write that down. So, affine transformation composition. Or let me say affine transformation multiplication. Or let me say composition. So let's say that A is one affine transformation, takes a V and sends it to LV plus lowercase a. And then I have B, another affine transformation, that takes a W and sends it to M W plus B. Here, L and M are linear transformations, and A and B are vectors. So now let's try to write down BAV. Okay? I want to see something like this. I want to figure out this composite transformation. So V starts here. And if I write it down, I get this. So first I need to apply A to V. Okay? So let me leave B as is and open up A. That gives me LV plus A, which then I can plug in as W to expand even further. So this would turn out to be this. M times LV plus A plus B. You know that matrix multiplication distributes over addition. So this is like this. MLV plus MA plus B. So this is a linear transformation, right? This is just a matrix multiplication. And now here, I'm taking a vector, applying the matrix to it. So now this is again a vector, and adding another vector to it. So this is a vector, this is a linear transformation. That is to say, the composition or the product of two affine transformations is an affine transformation. Just like how the product of two linear transformations is a linear transformation. So BA is also an affine transformation. Okay? Any questions about this? Now, instead of writing affine transformations like this, I can also sort of compactify a little bit the notation. And I can just say A equals L comma A, because an affine transformation, after all, is defined by a linear transformation and a vector. So I can put them in a pair and sort of simplify the notation a little bit. So A is L comma A, and B is M comma B. And let's write down this multiplication as well. Then BA equals M comma L times L comma A. It's a multiplication, and the way this should multiply should end up with this. That is to say, it should end up being this. ML in the first coordinate, and in the second coordinate, this. Okay? So you see, this rule really tells you how to combine two affine transformations. First coordinate is like linear transformations, and for the second coordinate, you're going to do an addition, but you need to take this matrix and change the second entry, second vector, a little bit using it, and then add. So if you want, this is sort of like a twisted addition. This is what people would say in the literature. So this is something like a twisted addition. Twisted addition, matrix multiplication. Okay? Okay. But as you can imagine, writing things out like this can get cumbersome. Okay? Because of this twist here, this first coordinate is always nice. It's like a matrix multiplication. But the second coordinate, you end up needing to keep track of how to twist which vector by which transformation. And so now our aim is to figure out a way to store this multiplication, affine transformation multiplication, inside matrices. Okay? So in problem set 3, there was this problem about storing complex numbers in matrices in such a way that complex number multiplication corresponds to matrix multiplication. I want to do the same thing here. I want to store affine transformations in matrices in such a way that matrix multiplication keeps track of this rule for me. Okay? Let me write this. Now what I want, store affine transformations in matrices so that affine transformation multiplication and of course also addition. The sum of two affine transformations is certainly affine. And addition is modeled by matrix multiplication. And addition. Okay? So any ideas? Let's start with 2 by 2. How can I store an affine transformation of the plane in a matrix? So a typical affine transformation looks like this. A, B, C, D, x, y, plus fg. So if I wanted to write it out, I would get this. ax plus by plus f in the first coordinate, and then cx plus dy plus g in the second coordinate. Any ideas? So I need to be able to store 6 numbers, right? For 2 by 2, I have 4 numbers coming from the linear transformation part and 2 numbers coming from the translation part. To compose, to compose 2 affine transformations, the inputs and outputs have to be of the same dimension, which means that I need to store these in a square matrix. In 2 by 2, I cannot do it, because in 2 by 2, I have only 4 spaces, not 6, which means that the next guess is 3 by 3. Okay. Let's not worry about the fact that now the input of a 3 by 3 matrix is a 3-dimensional vector, and we have 2-dimensional vectors. Any thoughts? Well, I can do this. I can do this perhaps. I can write this like so. Right? Now, this doesn't quite cut it because the inputs and outputs are not the same, but certainly I can take this, put it in my matrix. Okay. I still don't know what to do to these three entries, but this splitting suggests that the input xy should really be represented as xy1, which does make sense here. So I want this to be the matrix of my affine transformation. And when I apply it to this, I want to get something of the same type, right? The output is this. This plus by plus f cx plus dy plus g. So let me perhaps split it like so, because this is the original vector part, and this I just added. And the third one should be a 1, right? Because the input and output should be something of the same type. If I'm modeling a two-dimensional vector as a three-dimensional vector like this, the third entry is 1, certainly the output of the affine transformation should be, again, of the same type. Because otherwise, I wouldn't be able to keep applying affine transformations. Well, if this is the case, can I figure out, so what can I put here? Any ideas? Zero, zero, one. Okay? So now note that if I were to model my affine transformation like this, it does indeed keep track of this multiplication for me. So I can write then A like so. You see here, ABCD is the linear part, and FG is the translation part. So I'm going to split my matrix like that. Linear part, translation part, this is some 0, 0 so that things work, and this is 1 so that things work. Okay? So this is, using that notation over there, LV 0, 1. I'm lumping 0, 0 as the 0 vector. Oh, sorry, this is A. And B, maybe I should write it like this. B equals MB, and by the same schema, I'm going to get M B 0, 1. Okay? So now let's really verify that when I multiply these two matrices in the correct order, I do get the correct affine transformation. So I want this. BA equals BA, which is given by this. ML MA plus B 0, 1. Let's start. I'm going to open up these entries and write this down explicitly. And this is also good practice for matrix multiplication. This really is M11, M12, M21, M22, B1, B2, 0, 0, 1 multiplied by L11, L12, L21, L22, A1, A2, 0, 0, 1. Okay? Eventually I'm going to stop mentioning this, but again, yet another case of matrix multiplication. Left one I lump into rows. Right one I lump into columns. And now I get to multiply. The end result is going to be a 3 by 3 matrix. Oop. M11 plus L11, sorry, M11 times L11 plus M12 times L21. This is B1, but you see, we put 0 here, so that there is no contribution coming from there. Here I have M11 L12 plus M12 times L22. Here I have B1, of course, but again, this is 0, no contribution. Okay? Now the third is M11 times A1. I'm out of space. Let me write this somewhere else. Let me just fast forward this bit again. One, two, plus M12, L22, M11, A1 plus M12, A2. That's the first row. Second row, again, is the same. Let me not write it. Here you see I'm going to get just M21, A1 plus M22, A2. In the third row, I'm going to get 0 plus 0 plus 0. 0 plus 0 plus 0. Then 0 plus 0 plus 1. Now note that here we just duplicated this matrix, M times L, and here, oh sorry, I made a mistake. So when I'm multiplying this row by this column, B1 is contributed. So there's a contribution of B1. B1 here, and then there's contribution of B2 here. In short, it is indeed true that if I were to store my affine transformations in these matrices like this, matrix multiplication models for me affine transformation multiplication. Okay. That's that. And this is this. So if you want, you could think of 2 by 2 affine transformations, or rather affine transformations of the plane, as specific 3 by 3 matrices. Okay? And let me also say this. I really didn't want to, I didn't really need to open up these matrices and actually write down the multiplication. So just take these matrices and pretend that these are numbers. Okay? So, note, first row, second row. First column, second column. This by this plus this by this gives me ML. This by this plus this by this gives me MA plus B. This by this plus this by this gives me 0. This by this gives me 1. Okay? So really, I didn't need to open up the entries. I can really think about matrices with matrix entries. Okay? Matrices with matrix entries are called block matrices or partition matrices. block matrix or partitioned matrix. Partitioned matrix. Partitioned. Okay? And of course, it's all a matter of matching the inputs and outputs. Whenever you have, for instance, a 4x4 matrix, I can think of it as a 2x2 matrix with 2x2 entries. So I can write it like this. M 4x4 comma R, real valued, is the same thing as M 2x2 comma M 2x2 R, if I want it. Okay. In this case, the splitting is not standard, so it's not uniform. I'm not partitioning the matrix into 2x2 blocks. I'm partitioning it into one 2x2 block, one 2x1 block, one 1x2 block, and one 1x1 block. You can do a bunch of different things like this. Okay? And insofar as you're splitting the output of the first one and the input of the second one in the right way, you get to multiply the way I did multiplication here. You can just pretend that the entries are, so the matrix entries are really numbers, and you can do multiplication and addition as you would do with regular numbers. Okay? Any questions about any of this? Okay. So that was the case for 2x2. That was the case for affine transformations of the plane. So we said that the affine transformations of the plane can be stored in a 3x3 matrix. So how can I think of an affine transformation of Rn, n-dimensional space, as a matrix? Exactly. Exactly. So AV equals LV plus B can be stored. So can be stored in A, which is LB 0, 1. Now this is an n plus 1 times n plus 1 dimensional matrix. Okay. And the corresponding transformation of the vector, just like in this case we thought of xy as xy1, we can think of it as v as v comma 1 or v1. You just added one more entry to your matrix, to your vector, that is just 1. And this operation is called a homogenization, or you can say that this is v in homogeneous coordinates. Okay? This is v in homogeneous coordinates. And likewise, people also call this the matrix of the affine transformation in homogeneous coordinates. Okay? Good. Tomorrow we're going to keep working on this. I would like to discuss this perspective projection. It's another instance of affine transformation, but I think it's a good place to stop today. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. Today I'd like to keep discussing further stuff with affine transformations. Yesterday we talked about how translations is an affine transformation, and we learned about this homogeneous coordinates. There's another transformation that is very useful in computer graphics, namely perspective projection, and it turns out that that too involves affine transformations. We're going to get to that, but before delving back into affine transformations, I wanted to say a couple more words about this block matrices. So recall that this was, you can think of it like this. Either it's a matrix, a block matrix is a matrix whose entries themselves are matrices or vectors, or you can just think of it like this. Somehow there's a partition. And the main idea here is that you have two matrices, A and B, and of course I'm assuming that the output of B, number of rows, matches with the input of A, number of columns of A, so that this AB makes sense. But further, if the splittings match, you can also block multiply. That is to say, you can take the matrix lumps and treat them as numbers. So here's a picture. So I want the output splitting of B. In this case, that means I'm looking at this splitting. Okay? I want this splitting to match with this splitting. If this is the case, then you can block multiply, and at the end you're going to get a matrix whose input splitting matches with the input splitting of B, and whose output splitting matches with the output splitting of A. So let me color code all this. So let's say this is, so these numbers, these letters I'm going to write down represent the number of columns in that piece. So I want to say, for instance, here there are A columns, and then there are B columns here. And then let's say there are C rows here, and then there are D rows here. So that is to say, I have here a matrix of dimension C by A, and then here, for instance, I have a matrix of dimension D by A, and so on. Okay? I want this splitting, right? I'm thinking of this as like channels. I have, coming out of B, I have two different channels. One has C dimensions, the other one has D dimensions. I want this splitting to match with this splitting. So this is, again, C I want, and this I want to be D. And it turns out, in this particular case, the output of A is split into three channels. Okay? Let's say CD, E, F, G. If this is the case, I'm saying you can block multiply. And for instance, I can take this first row, so to speak, whose entries are matrices even of different dimension, and I can take it, multiply it this way. This by this by this gives me a matrix, and I put that matrix here. I'm going to do a more explicit example in a second, but this is just the main idea. And the input and output splitting of the end result is this. So the columns of the first matrix goes to the columns, and then the rows of the second matrix, the one that you're applying later, goes to the product. So this is E, F, G. So here's an example, for instance. Wrote down an example here. Yeah. So let's consider this, for instance. Okay. So A, let me say, is 3 by 5, and B is 5 by 2. I know now that when I take this product, it's going to be a 3 by 2 matrix, right? So the number of rows of B has to match with the number of columns of A. And when I do this multiplication, the end result is going to have 3 rows and 2 columns. There is no splitting it. But now let's introduce some splitting. And so I can I can write it like this. Instead of writing 3, I'm going to write 2, 1 to represent that the output of A is split into 2 dimensions and 1 dimension. And then in the middle, I have 3, 2, and then let's say that the input of B is not split. Okay? In this case, I just get AB, whose input is not split. It has 2 dimensions, whose output is split into 2. So let's write this down explicitly. I'm going to start here. So A times B is 3 by 5. Sorry, A is 3 by 5. So let's draw it like this. 1, 2, 3, 4, 5. This is A. Okay? And then B is 5 by 2. So 1, 2, 3, 4, 1, 2, 3, 4, 5. It's like this. And these splittings really tell me to lump certain entries of A. Okay? It is telling me first look at the first 2 and then put a separator here. Okay? And then the output is split by 3, 2. So split like this. Okay? Now the columns of B are not split, but the rows of B are split in exactly the same way. Okay? So 1, 2, 3. Okay? So now I can call this entry, for instance, A11, A12, A22, A21, A22. And here I can call this B1 and B2. Now the end result of this, according to this rule, is going to be a 3, 2 matrix whose input is not split, but whose output is split. 2, 1. Okay? So now I pretend that each of these matrices themselves are numbers, and here as well. And so what I can do is this. I can take A11, multiply it by B1. Okay? Note that A11 is 2 by 3, and B1 is 3 by 2. So when I multiply them, I'm going to get a 2 by 2 matrix. Okay? Which is the number of slots that I have here. And here again, I have a 2 by 3 matrix, and I have a 2 by 2 matrix. There's an error somewhere. 1, 2, 3, 4, 5. Drew it wrong. One, 2, 3, 4, 5. Should be like this. Okay. So now it makes sense. Okay. So A12 is 2 by 2. B2 is also 2 by 2. So the product is going to be 2 by 2. Again, I have 4 slots, and I can add it to here. Okay. I keep going. Now I have A21, which is a 1 by 3 matrix, and I get to multiply it by B1, which is 3 by 2. The end result is going to be 1 by 2. Okay? And finally, I have this, which is a 1 by 2 matrix, right? This is a row vector if you want, multiplied by 2 by 2, it's going to give me 1 by 2 again. This is the idea. Now the point here is that, of course, you don't need to sort of keep track of all this in general. You can just write everything out explicitly and just do regular matrix multiplication. The idea is that either way, you're going to end up with the same matrix. Okay, so you can just start with like this, entry-wise. You can multiply all of them and add them up and put it into this entry and so on. The idea is that you can do it that way, or you can block multiply to get this, and it's going to be the same thing. The benefit of doing this is to be able to use much more efficiently, perhaps, this data structure, so to speak. Okay? So, for instance, in the case of affine transformations, what we did was we sectioned off a certain matrix this way, and we were able to, using this particular shape, we were able to store an affine transformation in the matrix. Okay? In such a way that matrix multiplication corresponded to multiplying affine transformations. So this is sort of one of the uses of block matrices or partitioned matrices. Okay? Any questions about this? Okay. So now that we've been talking about splitting inputs and outputs of a transformation, I think it is time to introduce some more notation. Likewise, I want to think about split vector spaces. And this is the formalism of the so-called Cartesian product. Okay? So, split vector spaces. I'm just going to write it like this, okay? So far, our primary example of a vector space is Rn. Well, I'm going to just put across, okay, Rm. And for me, this is just going to be the vector space of ordered pairs of vectors. Okay? So x, y, this is ordered such that x comes from the first input and then y comes from the second input. Okay? Now this is essentially the same thing as Rn plus m, but really I want to keep this separation. I want to say that this is my first channel and this is my second channel. It just happens to be the case that my first channel is n-dimensional and my second channel is m-dimensional. Okay? Now this later evolves into more sophisticated things, tensor products and direct products, but for now, or direct sums, for now, let's just focus on this. So this is just an ordered pair of vectors. Okay? And so, of course, Rn, or let me say R2, is really the same thing as R times R. The perhaps distinction between these two is that when you're thinking of this R2, which is what we call the Euclidean plane, it doesn't really come with this coordinate system. But when I'm talking about this split R2 into two channels, I really have a horizontal and a vertical. And likewise, when I'm thinking of this, I'm imagining it as a caricature like this. The horizontal sort of hyperplane is Rn and the vertical is Rm. Okay? This is a caricature, of course. N is probably like 5-dimensional and so on, but still it is very useful to be able to draw caricatures of what is happening. Okay? Any questions about this? Okay.
I-
Yes.
This might sound silly, but what is an ordered pair of vectors? Like, what does that mean?
Yeah, I mean here that xy is not the same thing as yx.
But I guess like if you had a three-dimensional vector paired with like a four-dimensional vector,
Uh-huh.
what would that mean? You know what I'm saying? Like they're, what would that mean?
It means, for instance, this. Okay. Here I paired a linear transformation and a vector, for instance.
Okay.
So here I can write it like this. A is in linear Rn to Rn times Rn. It just allows you to keep track of a bunch of different objects together.
This is kind of just like for bookkeeping.
Yeah, as with the rest of linear algebra.
All right.
It's all about bookkeeping, yes. Yeah. Yeah, one technical matter, actually, that somewhat matters in certain contexts is that this notion of a basis really uses an ordered set of vectors. But we're sort of saying it's a set of vectors. So when you're talking about the set of something, or a bunch of things, the order doesn't really matter, in which order you're taking the vectors. Certainly, if you take a set of vectors, it doesn't matter in which order you take them, whether or not they're a basis. But when you change the orders of vectors, what the basis is actually changes. We're going to get to that later. So far, this is just a gadget that allows you to keep track of what is happening in two different channels. Okay, it's bookkeeping. Yeah. Yeah, it's like this. So I don't want to think of this as just a, for instance, n plus 1 times n plus 1 matrix. I want to say, oh, you know, this is a very specific matrix. It really came from this idea of this affine transformation. Okay. You see, this is really keeping track of that. When I say, oh, an affine transformation is in this space, it is telling me that affine transformations are determined completely by one linear transformation and a vector. But when I say an affine transformation of the plane is a 3 by 3 matrix, what is that? It's like, you need to say more, right? You need to say, oh, it is in this specific, it has to be partitioned in this way. Yeah. Any other questions?
So is the, when you write V to V1, is this V and 1 this ordered set of vectors?
So this, yeah, so you can think of it like a, so we're thinking of vectors as column matrices, right? Column vectors. And so this is really a block matrix, right? So this really means if V is V1, V2, dot, 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 Vn, I'm really thinking of it as an n plus 1 dimensional vector. This is the so-called homogeneous coordinates. This coordinates really allow me to think of an affine transformation this way. So V1 really is this block matrix notation. Okay, so this just means V1, V2, dot, 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 Vn, 1. So I'm thinking of this as a matrix whose output, right, is split as n1, and input is just 1. Any other questions? Okay, so yesterday we did a bunch of examples with 2 by 2 affine transformations or other affine transformations of the plane. Let's look at a couple examples of affine transformations of the three-dimensional space, because that is also very important. Now, in the case of the affine transformations of the plane, we ended up using a 3 by 3 matrix. Well, by analogy, that means that to talk about affine transformations of the three-dimensional space, we need a 4x4 matrix. So again, I can write it like this. So A x, y, z is going to be some linear transformation 3x3 applied to x, y, z plus a vector with 3 entries. Okay? It's a linear transformation. Storing this in homogeneous coordinates, we have this, right? A equals L, B, 0, 1 in block matrix notation, which really means this. So I have 3x3 coming from here. Okay. So this partitioning corresponds to this partitioning. This 0 is the 0 vector or matrix, which means that all the entries are 0. This is just 1, the number 1. And B has entries here, B1, B2, B3. And here are the 9 entries of L. Let me not write it explicitly. So L1, 1, and so on. OK? And I want to think of a three-dimensional vector, x, y, z, as a four-dimensional vector in the form x, y, z, 1, in analogy to that. So OK? Why am I doing this? Because since I'm interpreting the affine transformation as a 4x4 matrix now, its inputs and outputs are also 4x4. So somehow I need to come up with something here, right? So I need to transform this 3x3 three-dimensional vector to a four-dimensional vector. And it turns out that this is the way to go. So let's think about a translation. So the example in the book, let me see. So for instance, let's think of the affine transformation that corresponds to translation by -6, 4, 5. B, which is -6, 4, 5. So in this case, the linear part, so L over there is just identity. So if I write it like this is just like this, okay? A of x, y, z in non-homogeneous coordinates is just I times x, y, z plus this vector, 4, 5. So the end result is x minus 6, y plus 4, z plus 5. Now recall, yesterday we mentioned this idea that this vector that you're adding after applying your linear transformation really is where A, the affine transformation, sends the origin to. Okay? Because if I were to plug in x equals 0, y equals 0, and z equals 0, I would get -6, 4, 5. We did this in 2 dimensions. In 3 dimensions, it works the same. So B is where A takes the origin, the 0 vector. And of course, in homogeneous coordinates, A looks like this. I first separate it. I know that it's going to have 3 zeros here, no matter what the transformation is. This is a 1. So here I'm going to put B. And here I'm going to put, what should I put here?
Isn't it the identity?
Yeah,
It'd be
right?
1, 0, 0.
Exactly. Okay. Yes.
So if we're not given an L, like when it says translate by like whatever, do we just always assume it's identity?
Yeah, so if it's just a translation, that means that there's no linear part.
Okay, so if like there might be problems where it's like translate by B of whatever, like L is equal to this, and that's like we translate by L, or is it always going to be the identity matrix?
Well, if it's saying translate by this vector, that means that the linear part is always identity. It might say something like this. First translate by this, and then apply this other linear transformation. Right? So it could say something like, first translate by this vector, and then rotate by 60 degrees. Or it could say, rotate the three-dimensional space around this particular point. Not at the origin, but some other point.
So then how would you do that instead of having that identity? Would your A in the homogeneous coordinates, just where the identity is, you just put in whatever the L is?
Yes.
Okay.
Yeah.
So there's not like really a calculation that we have to do if we have an L?
There might be a calculation. We're going to see an example in a second.
Oh, okay.
There's always possibly a calculation. It depends, really, whether or not you should be doing a calculation. It depends on what the question is, really, right? So, let me do a 2x2 example, for instance. Just to give an example of this idea of encoding a transformation in a matrix, or as an affine transformation. So let's say that I want to look at the transformation that rotates the xy plane. So it's a 2x2. So it's a two-dimensional transformation along 1, 1, or around 1, 1. A from R2 to R2 rotates the plane around 1, 1. Now we know how to handle rotations around the origin. That's just the rotation matrix. But now the center of rotation is different. Okay, so let's think about this. Okay, so note that in particular, A has to fix 1, 1 because it is rotating everything around it. Okay? What else can I do? Well, let's think of this. If A is allegedly rotating the plane around 1, 1, it should be the case that this unit vector starting at 1, 1, at the end of A operating on the plane should end up vertical, right? So 1, 1 is going to be fixed. The point 1, 1 is going to be fixed, but this horizontal vector is going to be rotated vertically. And likewise, the vertical arrow is going to be rotated, and now it's going to look like this. Okay, does this make sense? Okay. If I were to just apply rotation by 90 degrees, right, so rotation by 90 degrees is just a cosine of pi over 2 minus sine pi over 2 sine pi over 2 and cosine pi over 2. Of course, you don't really need this formula, but let's remind ourselves. So what is this? 0, right? Sine of pi over 2 is 1, so minus 1, 1, 0. You see, this matrix does not quite do what I want, because it is rotating everything around the origin. In particular, it is not fixing 1, 1. It is moving it somewhere here. But what I can do is this. I can first, to understand this A, I can first translate this point back to the origin, then apply my translation, then bring this point back to where I want it. Okay? So let's have here translate let me write it like this. From here, I want to take this point to here, to the origin. Now I can rotate things. Which does what I want. This is just a linear transformation, because it is around the origin. And then I can translate it back. Okay? So I'm thinking of A as a composite transformation. Now, rotation is linear. Translation is not linear. It is affine, though. You see? And we realized yesterday how composition of affine transformation is an affine transformation. So at this stage, what we can say is that A indeed is an affine transformation. Now, I don't have the formula yet, but at least that's a statement. Is an affine transformation. Does this make sense so far? Any questions about this point? Okay, so now all that matters, so all we need to do is to write down the corresponding matrices in homogeneous coordinates, for instance, and then I can multiply things. Okay? So, I know that it's a product of 3 transformations. They are transformations of the plane, which means that in homogeneous coordinates, they are 3 by 3. So I have 3 matrices like this. So this corresponds to the first translation, this corresponds to the rotation, and this corresponds to the second translation. Now I know that the middle part has a linear part, it's the rotation matrix, but it has no translation. Okay, so this is 0, 0. And I know that here should be the linear transformation, which we computed to be 0, -1, 1, 0. So that's the middle piece. How about this? Any ideas as to how I should fill this in? So I need 6 numbers here. And these 6 numbers is supposed to correspond to this first translation. Yeah.
You could do identity on the left side, so 1, 0, 0, 1, and then -1, -1 on the
Exactly, right? Because the thing that you're gonna put here is gonna be where the 0 is being sent to. But then if you're translating 1, 1 to 0, 0, certainly 0, 0 is being pushed to -1, -1. So this is -1, -1, 1, 0, 0, 1. How about this? Question? Any ideas? So this is supposed to correspond to this one.
I kind of think it might be wrong, but I think it might be the identity and then like +1, +1.
Exactly.
Even though you're like rotated, like even though like in my mind like the y-axis is now like different, you know what I'm saying?
Yeah.
Like you don't care about that?
No.
Okay.
Because these are operating in 3 dimensions. You see?
No, I don't.
Okay. So the idea is this. I'm really modeling this 2-dimensional plane as a certain plane in 3 dimensions. So instead of looking at this plane here, I'm looking at the plane at height 1. Right, so thinking of xy as xy1 is the same thing as thinking of a point in the plane as a point in this particular plane in 3 dimensions.
I guess I was just wondering, like post-rotation,
Yes.
we all see that like the origin is going like over 1, up 1.
Yes.
But post-rotation, is that like as if it was going like down 1, over 1 or something? But it's not, so it's okay. So it's not. Yeah, never mind.
Are you comfortable with this part?
Yeah.
Okay, so you can think of it like this. This is an elementary matrix, and we saw how the inverses of elementary matrices are the same thing, except that you put pluses, or you change the sign. Okay, so the inverse of this is this.
Makes sense too.
Okay, so you're translating 1, 1 to 0, 0. Certainly the inverse of that should be translating 0, 0 to 1, 1.
Yeah.
Okay?
Are you wondering about like because the rotation matrix puts the y into the x position and the x into the y position? Are you wondering if like that stays like the y position?
Yeah, I think that was kind of where my head was at.
Oh, okay, because not only so when you're translating, so in the context of affine transformations, you have one vector that tells you how to translate everything. Now, in general, it might be that you're translating one vector this way and another vector that way, but in order for something to be affine, you're translating everything by the same vector. Okay? So that means, for instance, that not only are you translating this point to this point, but the end of this red arrow to the end of this red arrow.
Right.
So everything has to stay fixed. It's an object. It's a rigid motion. It's an object that you're moving in space.
Yeah, I think another kind of it says rotates the plane, but you're not literally rotating the plane. You're rotating the things in the plane.
Okay.
On the plane, not the plane.
Okay, so mathematically speaking, the plane is the things in the plane. There's no difference between them.
I guess. Yeah.
The thing is like parts and wholes are the same thing.
Yeah.
Yeah.
Right on.
Yeah.
So you're rotating the points, you're not rotating the xy axes. You're rotating the points. You're leaving the xy
Yes,
axis,
sure.
xy.
Yes, yes. I mean, the xy axis, the plane doesn't actually know that xy axis is there. I'm imagining it is there.
Yeah. I think I got it.
Yeah, there's a bunch of like philosophical stuff going on underneath all this, but the claim, the motto is that nothing makes sense and you just get used to it. Okay. Von Neumann. This is attributed to von Neumann. Okay, so once I multiply all this stuff, I should get the affine transformation that corresponds to A. Okay? So now let's multiply. And of course, when you're trying to multiply things, you don't really need to keep track of these partitions and so on, but it's a good idea because I have sort of like, I can think of this block matrix multiplication, and it somewhat makes things faster. So I'm going to leave this aside for now, and let me multiply this. This by this is going to be just this, because this is identity. 0, minus 1, 1, 0. This by this is going to be, so this by this is 1. This by this is minus 1. This by this is 0. This by this is 0. This by this is 1. And I know that these are going to end up 0, 0, 1. So you see, again, this by this, because this is identity, is just going to be 0, minus 1, 1, 0. This by this, I hope I'm not making a mistake. Yeah. Say again?
On the third row, instead of minus 1.
Third row? Where?
On the second matrix?
This?
Yeah, the minus 1 on the right-hand side should be plus 1 because it was minus 1 times minus 1.
No. So this by this is plus 1.
Oh, yeah.
This by this is minus 1. Oh, this is this is a minus 1, I guess. This.
No, you're right.
Oh, you're right. Yeah.
Now I'm questioning this one. How is this right? Because I'm multiplying this by this, no? Say again?
To get the bottom right corner, isn't the bottom row?
Oh, yeah, sorry. Yes. This by this is 1. Okay, it's correct. I was like, because it should end up with, it should end up in this form eventually. This is an affine transformation. This is an affine transformation. This should be an affine transformation. So it should be of this form. So that's why I was getting confused. But yeah, thank you. Okay. So finally, we have the vector part here. So this by this is 2. And this by this is 0. Which means, really, this affine transformation can be interpreted like this. My affine transformation A really is first rotating by 90 degrees and then translating everything by 2, 0. So A is the same thing. Same transformation. That first rotates by 90 degrees, then translates everything by 2, 0 to the right. A is the same transformation that first rotates, then translates by 2, 0. Okay, can we see this? Now, this is at 1, 1, which means that this degree is pi over 4. When you rotate it by 90 degrees, this is just going to go to here, rotate around the origin. But then when you shift it to the right, you get back this thing. Okay? And so it's the same thing as rotating everything around this particular point. Does this make sense? Okay. Yes.
So written in like the non-homogeneous coordinates, is it going to be like a of x, y is equal to the 0, -1, 1, 0,
Exactly.
x, y plus 2, 0?
Yeah.
Okay.
So in the standard coordinates, I would write it like this. A of xy equals, like your colleague said, 0, 1, 0, -1, 1, 0, xy plus 2, 0. And if I really wanted, I could also consolidate everything here, minus y plus 2 and x. Of course, it's not at all clear that this particular map does this, but it does, apparently. Okay? Any other questions about this? Okay. I think we're not going to do perspective projections, but we will do more examples of 3D affine transformations. And one very important class is 3D rotations. We talked about 2D rotations. There are also 3D rotations. We're going to be able to discuss this or see this later, perhaps. But it turns out that any 3D rotation, so you take, let's say, a ball in 3 dimension, and you're moving it around like this. Okay? Turns out that any 3D rotation is really a 2D rotation along an axis. So this is the Euler theorem, Euler's angle theorem, or rotation theorem. Any 3D rotation is along a certain axis. So there are, in the standard coordinates, of course, I have 3 different axes. So I can think of rotation along x this way. I can think of rotation along y this way. Or I can think of rotation along z. Okay? So you would say rotation along x is, for instance, is what is called roll. So this is called roll. Rotation along y, right? So I'm doing this. It's called the pitch. And rotation along z has anyone heard the third? Yeah, exactly. Now here, I'm imagining that, let's say that I have a plane and it is pointing along the x direction and its wings are along the y direction, okay? It turns out that in computer graphics and even based on the program that you're using, the conventions change. But roll is really rotation along the axis that you're pointing, that you're looking at, or that your plane is looking at. And pitch is your wings, and yaw is turning left and right. So this is also in the context of robotics and everything. So I'm just going to draw something like this. So you should really be thinking of a plane like this that is pointing in the x direction, whose wings are along the y direction, and whose wings, whose top is along the z direction. Okay. let me just write one of these. For instance, how can I write down the matrix for a rotation? This is a linear transformation after all. Well, a rotation along x, right? It's moving this way, which means that it is not doing anything along the x direction. That is to say, this has to be a matrix that fixes the x coordinate. So for instance, this would be represented by this. 1, because this is the x direction, and then r theta. This is linear, okay? And if you wanted to think of this as an affine transformation, you would turn it into this. Okay? If you want to fix z, so you're moving this way, you have to put 1 here and your rotation matrix here. And let me leave the case for the y-axis to you. Okay? Any questions about this? So, and that about covers the topics for the first midterm. We're not going to, so you're not responsible for perspective projections because we didn't have time for that. Maybe later we're going to return to it eventually if you have some time. Tomorrow we're going to have a review. It's not going to be recorded. Come with questions so that we can work on things, okay? Thank you. I'll see you tomorrow.